All right, here is something pretty new. This is what we call a parametric equation. And unlike what you've done work with before, drawing in the Cartesian plane, there's a new parameter called t that's in there. And the idea is that as t changes, you actually have x, y, and in this case z, because you're in 3 dimensions, and you plot those points and they form some kind of curve or line. So that's what this is. I'm going to do my best to draw some pictures so you can see what's going on. So I've got these 2 points, A and B, and you want to find a vector equation of a line that starts at point A and goes through point B. And it gives you a hint, but here's what's going on. I tried my best to draw this. I'm not the expert at drawing these things, but there's a nice Khan Academy actually where they draw these things out. So the first point is -4, 2, and -3. So I have x is to the left and right. It's like the Cartesian plane that you had up on the wall is now the floor. So x is left and right, y is front and back, and z is the elevator that goes up and down. So z is where y used to be. In physics, you actually have y where z is, so that's actually probably the right way to do things. But this is how we do it in math. And that'll probably be the last time I say that physics does it better than math. That's usually not the case. All right, so what do I need? If I want to find the parametric equation of a line, things are not so simple in 3 dimensions. You don't have y equals mx plus b anymore. So what do I need to do? I need 2 things. I need something called a position vector and a direction vector. What's a position vector? Well, if I take starting at the origin and I go up to point A, that's an example of a position vector. I've now found a way to start from the origin and end up at the line. So now I'm down here. If I consider this endpoint a pencil and I drew it back and forth across the line, that's multiples of what we call a direction vector. So right here goes up the position vector. That's the formula for this. I actually should have written the formula up here. Maybe I'll quickly draw that so you can see it. So the formula for a line, let's see if I can do this quickly, is not y equals mx plus b. It actually looks like, in parametric form, what it looks like, it's going to be a position vector, r sub 0 plus t times a direction vector. And we use these letters in your book. So on the t and everywhere you see it, that's going to look the same. It's going to have a position vector plus t times a direction vector. So what I just gave you was the position vector. It starts at the origin and the tail of it ends at the point A, -4, 2, and -3. And I could have had it do it to B. It's not unique. So I have -4, 2, and -3. I'm not sure what would happen if you put, I guess that's why they said start at point A. So that goes here. Now what goes here? How do I find the direction vector? First, I take the point, they gave you this hint, but I take the point A to be the head and the point B to be the tail. So I did that, and I find the vector between the points A and B. How I do that is I go tail to head. So I take the point 7 and subtract the point 4, -4. So I'm very careful here with my minus signs because I make a lot of minus sign errors. As my section knows, I do this. 4 minus 2, -5 minus the -3. So I'm very, very, very careful in writing that down. So I get 11, 2, and -2 as the direction vector V. So what does that mean? I'm going to take a little time here to explain that. If I drew V, this is what V looks like. And now if I multiply that by a t, I looked at any multiple of that, it's going to actually stretch this whole line out because multiples of a vector stretch it out to the left and right. And so if this first teal arrow gets me up to the line, t times v stretches me back and forth across the line once I have a direction. And so that's what goes up here. It's the 11, 2, -2 that goes into this slot. And it looks like it wants it in curly brackets. So now you have the form of what is expected here. So I hope that's clear. Again, there's a Khan Academy video that's pretty short that explains this really, really well and draws a lot better than I did. But I hope you get the idea of how we can represent lines in 3-dimensional space using a parametric formula.